Thank you all for coming today. Well, I'd love to be with you in person. I am excited to be able to do this virtually, so many more of you can join. I do want to start by thanking my committee, Brian especially, for the 8 years that you've been providing me guidance. And then along with UW faculty Steve Brunton and Tim Munden, also at Acilla Power, and Matt Dunbabin, who courteously hosted me in Australia, and then John Delaney, my graduate student representative. So thanks to all of you for making this possible. I'd like to start this talk by acknowledging that this research took place on the traditional land of the Duwamish, Suquamish, S'Klallam, and the Coast Salish peoples. So I'd like to honor them past and present, and the land itself with my gratitude. And for those of you who are not in the Pacific Northwest, I highly recommend going to this website to find out whose traditional land you're currently on. So speaking of land, when we think of a map, we usually picture something like this. And in fact, it's equally, if not more valid, to picture something like this. If I can get my slides to go forward. In fact, our oceans cover 71% of the Earth. And whether you live in a landlocked state or on a coast, the ocean supports your life. At least half the oxygen you breathe comes from phytoplankton in the ocean, and the ocean stores solar radiation, moves heat and moisture around the globe, and drives our weather systems. On a coastal scale, our waterways provide numerous additional ecosystem services. They host shipping, fishing, recreation, and more recently, marine energy extraction. But in order to responsibly make use of these waterways, we need to understand the phenomena that are present in these systems, from the currents and marine weather impacting navigation, to upwelling and tidal flushing moving nutrients essential for fisheries. So to understand these phenomena, we need to make observations. And while I don't have time to discuss all the myriad ways we make ocean observations, I do want to point out one of the most revolutionary sensing paradigms of the last century, and that is the Argo Float, seen here deployed rather improperly off the side of a vessel. So the basic premise of the Argo Float, it's deployed gently from a vessel. It dives to a parking depth of 1,000 meters and drifts there for a number of days. After a predetermined time, it dives to its profiling depth, which is 2,000 to 6,000 meters, depending on the model, and then rises back to the surface, making measurements of essential ocean variables. This data is communicated back to shore via satellite, and then the process repeats. The resulting data is a look at the vertical structure of these essential ocean variables, particularly temperature and salinity. And since the program's inception in 1999, over 2 million profiles have been gathered, and there are nearly 4,000 floats active in our global oceans today, contributing to our weather and climate models. So I was intrigued by the possibility of taking this paradigm of distributed 4-dimensional sensing and scaling it down to coastal settings. While the spatial scales here are smaller and the water is shallower, as large-scale forces like tides interact with the shoreline and the bathymetry, so underwater topography, in these smaller spaces, that energy gets concentrated, which leads to strong gradients and fast currents. This is what tidal energy is looking to take advantage of. And these currents are a critical variable when we're interested in characterizing these coastal waterways. And it's not just for the energy extraction possibilities. Currents transport nutrients and pollution, which impact fisheries and recreation. They transport sediment, which changes bathymetry, which is of critical interest to mariners. So really, currents are a fundamental variable, and they drive the chemical, biological, and geological state of these ecosystems. So what devices do we have for measuring these currents? Well, one of the most common ways they're measured are using stationary acoustic Doppler current profilers, or ADCPs. These devices use sound to estimate 3-dimensional velocity at a series of points extending away from the device head. They can be anchored on the bottom as pictured, or mounted on surface buoys, and thus provide an excellent time series of local velocities, but at a restricted spatial scale. Now, X-band radar is a somewhat newer method. It uses the same marine radar used for vessel navigation to map the wave field. And using some smart processing, it can estimate the underlying currents based on how they change that wave field. Excuse me. While they offer an impressive horizontal coverage, mapping up to 4 kilometers of range from a single device, they can only measure the top few meters of water. And as you may expect or know from experience, water gradients are, vertical gradients end up being quite a bit stronger than horizontal gradients. And this is because water depths are typically smaller than the horizontal ranges. So they can be 50 meters steep as opposed to 5 kilometers wide. So since resolving both vertical and horizontal structures of interest, another common approach is to mount one of these ADCPs on a mobile platform, such as a vessel. Now, this improves the horizontal coverage over the stationary ADCP, but at somewhat reduced observational endurance. However, in marine energy sites, which was the lens by which I was approaching this problem, being a member of the Marine Renewable Energy Lab, the current field is evolving in a matter of minutes. So the time window that you have to make a set of observations that can be reasonably considered measurements within the same field, this window can be as short as 15 minutes, which really constricts the amount you can move around with that vessel. So given the success of the Argo program, using a multitude of passively drifting distributed sensor packages to provide both horizontally and vertically resolved data, we posed the question, could float swarms be adapted to coastal environments and simultaneously map these current fields? And that initiated this swarm sensing concept, which I believe I first drafted in 2015. So we've got a support vessel. It deploys a number of floats that descend to target depths. These flow along with a current and resurface after some pre-programmed time to be recovered. And then because we need to know the float position along the tracks, we're going to use an array, and because GPS doesn't work underwater, we need to use an array of surface drifters that are GPS tracked. And these are equipped with acoustic modems that communicate with the floats, also equipped with acoustic modems, to triangulate or trilaterate the float while it's underwater. So this was the basic idea of the research. And for today's talk, I'm going to be answering the following 4 questions. First, can float swarms work? Second, how do we design a coastal float? Third, how well do they function? And fourth, what do we actually end up observing with them? So let's start with that first question. Are float swarms even a viable option for mapping tidal currents? Before we invested in hardware, we wanted to know if float swarms could even work in these environments. In particular, I wanted to determine if the number of floats we'd need would be even practically feasible. And to assess this, I simulated swarms of floats mapping currents in the prototypical tidal channel shown. And I examined how reconstruction error changed with the number of floats in the swarm. Additionally, I looked at how many floats were needed to sufficiently cover the domain and determined that somewhere between 10 and 50 floats was sufficient for these 1 kilometer scale surveys. And this was the work I presented during my general exam. One of the questions in the subsequent discussions was, is this accuracy that we're seeing here reasonable? More specifically, how does it compare to the other accuracies of our other sensing methods? So I shifted away from that prototype channel and sought out a more realistic environment and collaborated with UW graduate Dr. Kristen Thing. And during her PhD, Dr. Thing built a high resolution simulation of tidal currents in Admiralty Inlet. Its outputs included 3-dimensional velocity data as well as water property data like temperature and salinity, on a regular grid with 65-meter horizontal resolution and 2 to 10-meter vertical resolution at 15-minute intervals over a period of 1 month. So a nice high-resolution environment in which to perform a virtual experiment. So we treated this simulated velocity field as the environment we're looking to observe, and I performed a series of virtual surveys. I looked at 24 virtual survey locations. Those are the black dots you see indicated on the map, and computed over 2 tidal cycles, 1 strong spring and 1 weak neap cycle, with each survey lasting 15 minutes for a total of 2,888 surveys. So in each surveys, I sampled the velocity field in a manner consistent with each of the floor platforms I showed previously, and included the relevant sources of error for each of those platforms, producing a volumetric reconstruction of velocity over a 500-meter by 500-meter volume at each of those survey locations. Now, while I don't have the time today to go into those results in detail, I will show you 2 major highlights. First, looking at the error for each platform computed across all of the surveys, we can see that the floats perform nearly as well as the mobile ADCPs. So here, 0 error or 0 difference is what we were looking for. But in this process, I also realized something that was somewhat obvious in hindsight, but definitely important nonetheless. And that's that the floats offer the additional benefit of being a truly in situ measurement. They're actually in the water, sensing the properties that are alongside it. This is unlike the remote measurements based on sound for the acoustic Doppler current profiler and the radar performed by the other devices. And that means that at the same time as resolving these tidal currents, the float can simultaneously resolve 3D maps of in situ water properties, like salinity. So to give you an example, here's the salinity during the neap cycle at one of those locations, as measured by the float that's the dotted purple line, plotted against the actual salinity in the solid purple line. And you can see that they're very close. The one separation occurs during slack tide, and this is actually a result of lack of sample coverage, as the flow velocity doesn't move the floats through the evaluation volume. So to summarize our answer to the question, can float swarms work for volumetric current measurements? Yes. And in fact, 30 floats is sufficient, and they offer concurrent mapping of in situ water properties. So the outcome of this work was published in 2020 in the Journal of Atmospheric and Oceanic Technology. And at this point, I want to pause and see if anyone has questions.
And those questions, you can unmute yourself to ask, or put a question in the chat, or raise your hand.
If you put a question in the chat, Brian, if you can monitor that, I would appreciate it, because it's hard for me to see. All right, no questions. Moving on. So, second question: how do we design a coastal float? So we're encouraged by these simulation results, and especially excited that it didn't require 1,000 floats. And this was practically feasible to go do this. So at that point, I set about investigating how to design a float swarm. So looking back at that original concept, I knew that the individual float needed to be inexpensive, and I wanted to target a swarm of 30 floats having a cost of about the same as a single ADCP, which runs about $60,000 to $75,000, which meant the individual float costs needed to be under $2,000 each. Next, I wanted it to be easily deployable by an individual, thus eliminating the need for any special vessels. Third, to get a reliable vertical distribution, I wanted depth control to within a ½ meter up to 100-meter depths. Since knowing the float tracks is critical to the data output and GPS doesn't work underwater, we needed some kind of underwater localization. And obviously higher accuracy is better, but we want the system to be able to resolve float positions to within the horizontal spatial scales relevant at these sites. So we felt that 10 meters was a decent target there. Additionally, I needed the float to be as float following as possible, so we're getting valid current measurements. And then finally, while the retrieval of Argo floats isn't really cost effective and they're just abandoned at the end of life, in coastal areas, our regions of interest are only a few kilometers long. So given the fast currents, floats may move through that region of interest in a matter of minutes, thus necessitating active recovery and redeployment. Additionally, we don't want to just be littering our shores with a bunch of small sensors. Now, there's some additional requirements that come out of doing that depth control. And to understand these, we need to take a look at the dynamics of buoyancy controlled floats. So the acceleration of a float is going to be a function of gravity pulling the float down, buoyancy equal to the mass of the displaced volume of the float pushing upwards. If there's any relative velocity, there will be corresponding hydrodynamic drag. And finally, the float is being ejected along with the surrounding flow. So accelerations of the water surrounding the float, so these are accelerations of water that's of a length scale greater than the size of the float, what you might call an engulfing gust, those will also accelerate the float. Now, they're buoyancy controlled floats. So let's take a closer look at the buoyancy part of this equation. So let's look at the state of neutral buoyancy. In this case, there's no acceleration, no relative velocity, and thus no drag. And we'll assume that we're in still water, so there's no movement of the surrounding fluid. We can't control that anyway. So in this case, gravity and buoyancy are equal and opposite. And by rearranging this expression, we can see that the float density is equal to the water density. To achieve buoyancy control, we're going to manipulate the float density to be more or less dense than the surrounding water so that we can move through the water column. And we do this by adjusting the volume of the float. You can do it with the mass, but most oceanographic floats use volume. So we can break the volume of the float into two components, the nominal volume V naught and the time varying controllable volume of the buoyancy engine VB. So how big does that buoyancy engine need to be? Well, it serves two functions. It needs to be able to automatically ballast the float, that is, adjust the density of the float to the local water density. And it also needs to supply actuation to move it up and down. So for a float deployed in a coastal environment, it may experience considerable changes in site density. Deployed at a river mouth in fresh water and transported into salty ocean water, the surrounding water density may change by as much as 3%. Thus, the buoyancy engine must be able to change the float volume by at least 3%. Now, beyond that, the float needs to have the additional capacity for actuation. So let's look back at the original dynamics expression. Again, we're going to ignore water movement, but this time we're going to break the buoyancy term into the ballasting and actuation components. Here, we've defined the nominal float volume and the ballasting component of the buoyancy engine to be equal to the force of gravity. So these terms cancel. And then in the case of no acceleration, the expression will simplify to a balance of the actuation volume and the hydrodynamic drag. So if we rearrange this expression, we can see that the terminal velocity of the float, U max, is a balance of that extra buoyancy engine capacity and the drag, with the area and the coefficient, that's A and CD, determined by the geometry of the float. For deployments in the fast currents that we're looking to deploy in, the float needs to be able to move to a depth in operationally feasible timescale. And so we targeted about 0.5 meter per second vertical velocities. So equipped with these requirements, the next logical question was, what floats exist? What can we use to do this? And it turned out that there were really only a few floats suitable for coastal applications. These included MRV Systems' Alamo float. This is a slightly smaller Argo style float. Eric DeSaro here at UW had been using his Lagrangian float in the upper ocean mixed layer for a number of years. Chris Roman and his group at University of Rhode Island were developing a similar float for coastal benthic surveys, and and it's slightly out of order. That's what I want you to see. And Jules Jaffe and colleagues at UC San Diego Scripps were developing their miniature autonomous underwater explorer for emulating larval transport. Now, I've given away the punchline here, which is really unfair. But while they're all great platforms, the first three were too expensive for swarm deployments. Now, Jaffe's, which was specifically designed for swarm sensing, was more promising at that 3K unit. But then when we looked at the buoyancy engine capacity, it was evident that only the Alamo floats would really be suitable for that full fresh to saltwater deployments. And Jaffe's float would really be restricted to relatively homogeneous environments and require careful ballasting. And that's when we thought, there's room here to expand the suite of available floats. And that's when we decided to develop the microfloat, which has been kind of the thrust of my dissertation. And in this case, we really beefed up the buoyancy engine, providing a 9% volume change. And this allows for actuation from fresh to salt water, actuation speeds upwards of 0.6 meters per second, and additional capacity for external sensors. Now, it took us a number of years to get to the current model, so I'd like to provide a quick history of the development. Oh, now I've done it. There we go. So in winter of 2016, why my slides are not advancing? All right, there we go. They're coming back. In winter of 2016, an undergrad capstone design team built the very first prototype, which successfully moved up and down in the UW Oceanography Department's saltwater tank. And taking lessons learned from their experience, I redesigned the float for the remainder of the year in anticipation of traveling to Australia to work with Matt Dunbabin at Queensland University of Technology. And we were hoping to use the floats to demonstrate navigation in a tidal environment by using the time-varying currents and just the vertical float movement to move from A to B. So actually doing navigation. Now, while we didn't quite achieve that due to slower than expected prototype development, we did finish that updated version of the float in spring of 2017 and did a number of pool tests and a single harrowing deployment in the Marucci River. So in autumn of 2017, I returned to the States and performed a couple more benchmark tests in Lake Washington and Chilchol Bay. We'd also gotten the good news that year that we received funds from the Office of Naval Research to build out a swarm of 30 microfloats. So in winter of 18, with a collection of APL engineers, I redesigned the float to improve manufacturability. And it was in that process that I specifically sought to increase that buoyancy engine capacity due to some ballasting annoyances that I had experienced in the previous tests. It was also around then that I had identified how significantly a high capacity buoyancy engine would improve the adaptability, the sensing flexibility of these floats. And so the outcome of that redesign is the current version of the microfloat, which you see here. So as I said previously, the float has a unit cost of $2,000 and an actuation of 9%. This is for a given the nominal float volume of 4,700 cubic centimeters or 4.7 liters, and a piston volume of 450 cubic centimeters. The float has a depth range of 100 meters and endurance of about 1 day. And for sensors, we're measuring external pressure. This is how we sense the depth of the float, as well as water temperature. Internally, we track float movement with an inertial measurement unit, and we also monitor power and relative humidity so that we can have the float recover if the battery is too low or we sense a leak. We also have an auxiliary port that allows for integration of those external sensors. So finally, for communications, we're localizing the float via GPS when it's on the surface, and this is communicated to the supervising vessel via radio and cellular modems. And when underwater, we're using an acoustic nanomodem to provide localization, which I'll discuss in a couple minutes. So construction of the swarm started in summer of 2018 and finished off in spring of 2019. And a particular highlight was getting to deploy in Squim Bay. This might be a little choppy for you all, but this is the proper way to deploy floats, unlike the Argo Float. And this is just throwing in that surface localization buoy that we do for the localization. So at this point, oh, skip that slide, go back. So at this point, we have 25 active floats with a few spares and 5 surface buoys for localization. So you're now probably thinking that all sounds great. Does it actually work? And I'm going to get to that. But before I do, I wanted to pause and see if anyone had questions at this point.
One question that came in through the chat was whether in the early days of this, you also had looked into any of the kind of micro UUVs that exist and whether they would be suitable for the sort of mapping process.
Micro unmanned underwater vehicle. Okay, so yeah, it's always a matter of figuring out which algorithm, not anagram.
Acronym?
Yeah, thank you. So kind of indirectly at a couple moments, but the big thing was the tidal currents that we're observing are upwards of 2 meters per second. And if you are putting, and the UUVs or AUVs, really only the very strongest of them have actuation, have propulsion that can overcome even 1 meter per second. And so most of those vehicles are in the ballpark of $100,000 each. There are some that are coming down in price now. But when you're talking about $100,000 drift, supposed to be propulsive systems now drifting through your channel, it's a little bit scary. So we decided, well, why don't we just have them drift? There's also a whole host of what's called Lagrangian analysis. So that's when you're, it's what the floats are. It's when they sit at a point and you watch what happens with the water properties as they flow along. So using a truly Lagrangian platform like the floats allows us to take advantage of that body of literature. I think that covers it.
Trevor, you got a couple other questions that have come in the chat. One is, how challenging was it to develop good seals in the buoyancy engine, and is the hull pressurized above ambient?
The hull kind of sometimes is above ambient and sometimes is below ambient, depending on whether the piston is in or out and how the temperature has changed. But we don't do any a special pulling of vacuum internal to the float. And in terms of sealing, we have had some issues along the way of sealing, although the piston seal at the bottom, we have not actually seen any problems with. We made a choice of a T-seal, which is a version of an O-ring seal around that when we started, and it worked out. So we haven't seen any issues there. But we have seen issues around our housing seals. These are commercially available housings that we're taking advantage of. And I think that there's some amount of variation there that causes some leaking. So.
And then you had one other question, which was there any need to consider temperature gradients in addition to salinity gradients when you were deciding on the actuation volume?
So in temperature gradients are definitely going to impact the overall density, but salinity is going to impact it by nearly an order of magnitude more. So really it's the dominant signal in these coastal systems driving density changes. Now, when you get into the open ocean, the salinity changes are much reduced, and actually the temperature changes are what dominate. But our buoyancy engine can already has the capacity to manage the range that is created by the fresh to saltwater salinity gradient. So it shouldn't have any problem with anything caused by temperature changes.
You're out of chat.
All right. So with that, I'll move along to how well do they function. So in particular, before we go off doing science with the floats, we need to ensure satisfactory performance of our depth control and underwater localization, because this is what our science is going to depend on. So we've undertaken a host of benchmarking tests to date to prove out those abilities. I'm going to take a sip of water. I should have done that before I transitioned. All right, so we've performed a number of tests in the Oceanography Department saltwater tank. We've deployed in the quiescent water of Lake Washington and Portage Bay, and performed tidal channels in Squim Bay, as I showed in the video, and more recently in Agate Pass, Washington. And in the process of these tests, we've amassed over 468 individual float deployments and lost only 3 floats along the way. An additional 2 floats were lost and subsequently recovered, which really proved the value of if lost, call me stickers and the kindness of strangers. Now, I obviously don't have time to present results from all of these today, so I'm going to focus on a couple key outcomes from Lake Washington and the oceanography tank and dive into the results from Agate Pass in detail in the final section of the talk. So let's look first at depth control for a float over its deployment in Lake Washington. Here, depth is going to be indicated on the y-axis with 0 meters indicating the surface and elapsed time on the x-axis. Here, the float has been programmed for a series of dives with a target depth indicated in light gray and the actual float trajectory indicated in dark gray. Now, revealing the full time series, we observed that the floats can successfully dive to and hold a range of depths. Now, this is just one of 14 floats deployed during the test. So to examine overall swarm performance, let's take a look at depth holding statistics across the floats and dives. And I'll actually slide some data in from Agate Pass as well. So relative to the target depth, the real trajectory may be slightly off. And here we're going to compare that settled depth to the target depth and compute offset. And we're going to plot the settled offset on the y-axis as a function of the step change performed by the float on the x-axis. And we see that the overall performance in both Lake Washington and Agate Pass, the offset is within 10 centimeters of that target depth. So that was extremely encouraging. And then we also care about the deviation around that settled depth, because we'd like those deviations to be near 0. So looking at deviations as a function of step change in both Lake Washington and Agate Pass, we do observe much larger deviations in Agate Pass. Now, this was due to the fact that Agate Pass is an energetic channel and there's vertical turbulence that moves the float away from its target depth. And thus the floats have to actively counter that in order to maintain their depth. In Lake Washington, the water is nominally quiescent or still, so these deviations are considerably reduced. But even in energetic environments, most floats are able to maintain depth within a ½ meter of their target, which is definitely sufficient for providing controllable distribution of swarm deployments. So next, one of the obvious advantages that I've advertised of the microfloat is that large. Lee, are you trying to ask a question, or did you just accidentally unmute yourself?
I'll go in here without you.
Okay. Now, obviously, one of the advertised advantages of the microfloat is this large buoyancy engine. Now, while we haven't gotten to the auto ballasting function in the field, we have performed a controlled test in the UW oceanography tank. So during this test, Cassie Riel and Ben Maurer added calibrated weights to the float. And so let's take a look at the results from those disturbance response tests. So here I'm plotting float depth in blue on the left-hand side, and on the right in orange is the piston extension. So more extension means more volume, means more buoyancy. The float is programmed to hold 1.25 meters depth for the duration of this test. So starting at 5 minutes, we gradually add 108 grams worth of weight to the float. And you can see the piston extending to compensate while the depth holds quite steady. So this 108 gram change equates to a roughly 2% density change in the water. So if we compute the extra buoyancy resulting from the change in the piston positions, we estimate that 106 grams of added buoyancy is now there. So the accuracy in our piston position really gives us knowledge of that extra volume only to within 5 grams. So to within our level of knowing, these are effectively equivalent. Now, as you can see, we still have plenty of spare capacity for actuation, and we've made use of that. So we've added both GoPro cameras and hydrophones to the exterior of the float for supplementary data during our benchmarking tests. And if we take a look at the associated depth performance for those floats with the external sensors, we really observe no functional difference relative to the unadorned floats, which are the gray you see underlying the colored lines. And I'll add that I didn't have to do any special tuning of the control algorithm to achieve this. I just needed to perform initial coarse ballasting of the floats, and only those with the hydrophone. So this really demonstrates the capacity of the float to handle external sensors. So to summarize the depth control performance, we're able to control depth within 10 centimeters of the target in quiescent water and within ½ meter in energetic flows, and this is over a range of depths. I've demonstrated the ability to compensate for site density changes. While I didn't have time to show it in detail here, we also have the ability to tune the transient response of the float. So this is the stage of the float moving to depth. And we do this by limiting how fast it descends and rises. And it helps to reduce overshoot past the target depth and improve the consistency of the settling time, the time it takes the float to reach its depth across variable ballasted floats. And then finally, I demonstrated the float's capacity to accommodate external sensors, which is a particular advantage of the adaptability of the microfloat. So again, I'd like to pause here to ask if anyone has questions on the buoyancy engine and the depth control.
Got a couple coming in the chat. So one is, can you elaborate a bit on your feedback control algorithm for depth?
Yes, and I meant to include this as a backup slide, but we are using a two-stage proportional derivative controller. So PID, proportional integral derivative controller, is a very standard linear control algorithm where you just have a series of gains that you apply to the current error, the derivative error, and then the cumulative error over time. And based on the addition of all those three terms, it outputs a do this command. And so we do two stages. First, we check the position, and that says, oh, we're ½ meter off. And then the next, we actually check the float velocity and say, okay, if we're a ½ meter off, we should be going 0.1 meters per second because we're trying to come in slowly to our target depth. So we have a two-stage system. And in that process, we can also do add a velocity limit. This is what I was talking about in terms of tuning that transient response. So we can say, okay, float, don't go faster than 0.5 meters per second. I know you can, but I only want you to go 0.2 meters per second because I don't want you to overshoot your target. Does that answer the question? Hopefully.
Yes. The second question is in regards. I'm going to slightly rephrase the question. It's a question of your uncertainty. How does the uncertainty in the water density and the variable density above the float affect your ability to understand what your depth actually is?
Yes. Okay. So I have glossed over that. So we're taking a measure of pressure, which is to within very close accuracy. If you're looking at decibars, nearly exactly 1 meter. We don't have a precise measurement of float density, of the water density. And so the cumulative density difference that can occur above where a float is can mean that you could potentially actually be deeper, might be deeper than you think you are. However, if you think about the depths that we're operating in, which is up to 100 meters, and the possible maximum difference that might occur is that you're sitting in this little lens of fresh water down at the bottom, and then you have salt water completely above you, or I guess vice versa. Salt water is lighter and fresh water is denser. And so you might be guessing what your density is, but at most by a factor of 3%. So you may be off. If say you think you're at 100 meters, you might actually be at 103 meters. And you could get around this by profiling and adding a conductivity sensor to your float, by which you could then compute a direct measurement of density. But for the sake of the accuracy of what we need to accomplish in terms of knowing the depths and knowing where to assign the data that we're gathering, we, at least to this point, ignoring that change doesn't result in too great a degradation in the accuracy of our system.
Or one final question, I think, before you move on to the next section is, based on the PD control, is there a way to tune the system based on the area you're deploying to remove and further reduce the overshoot?
Probably. It's not something I thought about doing. Generally, one of the, I can bring it up at the end, but if we bring the velocity limit down to 0.2 meters per second, we can effectively bring, even for 50-meter dives, we can bring that overshoot down to less than 2 meters. So you make it slower, it'll get to depth slower, but it'll also not have as much overshoot. So yes, you can tune, but in terms of modifying for the particular site, we haven't thought about it yet.
No further questions at this time.
All right. With that, let's move on to benchmarking our underwater localization. So the backbone of our underwater localization is the acoustic nanomodem, which is included on each float and each surface localization buoy, indicated by the arrows here. The nanomodem was originally developed by Jeff Neesham at Newcastle University, who was introduced to us by Tim Munden. And it was really quite fortuitous because the nanomodems are an economic solution as they provide an exchange of very short messages at ranges of, in theory, up to 2 kilometers, which is really a perfect fit for the microfloats. And our implementation relies on trilateration of the floats using exchanged timestamp messages from the surface buoys to the microfloats. So we know the latitude and the longitude of all the surface buoys from GPS, and we want to determine the horizontal position of the float. Each surface buoy broadcasts a coded ping, which is recorded on all the devices within range. And this proceeds in a round-robin fashion, scheduled based on the number of surface buoys deployed. In post-processing, we compute the distances between the surface buoy and the float based on the ping time of flight and the sound speed in the water, c. So for example, a 0.2 second time of flight and a measured sound speed of 1,500 meters per second, we compute the distance to be 300 meters. Now, by combining at least 3 distance measurements within a given time, we can trilaterate the float position. More surface buoys provide additional information and give rise to an overdetermined system that we can be solved using a least squares approach. Now, it's somewhat difficult to benchmark the localization accuracy given we don't know the true location of the floats. However, the nanomodems on board the surface buoys also record messages from other surface buoys. So for the sake of evaluating accuracy, we can perform the same localizations on the surface buoys. And we can compare the acoustic estimates to the known GPS location. Additionally, we can also use the distances estimated from the GPS data to simulate perfect acoustic distance measurements. So this allows us to distinguish what errors are due to inaccuracies in the acoustic channel and what errors are due to uncertainty in the trilateration algorithm. Because while the nice triangular geometry I'm showing here will result in decent localization accuracy, an array like this one is going to result in much greater uncertainty in the estimated position. So with that in mind, let's take a look at some data from Agate Pass. So here's an example of the surface localization buoy trajectories during one of the Agate Pass flood deployments. Here, the buoys were deployed up at the squares and then recovered down at the crosses. And what I'm going to show here, and what I'm showing here, are the GPS tracks. So let's take a look at the acoustic localizations. Here, the true GPS track that are in colors on the left-hand side are plotted in dark gray on the right-hand side. In light gray, we have the trilaterated GPS data that's using the quote-unquote perfect GPS distance, and then the trilaterated acoustic data in blue. And we can see that they're both quite noisy relative to the actual GPS track, but they are very close to each other. And that indicates that the acoustic distance measurements derived from the nanomodem pings are indeed accurate. And the error for the trilaterated estimates, especially at the start of the deployment, suggests that the geometry of the surface buoys is introducing considerable uncertainty in those localizations. This improves later in the survey. Now, since the raw trilaterated positions are suggesting physically impossible trajectories, we know that the floats don't move 60 meters in 1 second. We smooth them using a robust moving local quadratic regression. And that produces the orange trajectory shown here. If we compute the statistics of position area for each of the data sets, this is over all of the surface localization buoys, we see that 50% of the smooth positions are within 5 meters of the true position. And since we're ultimately attempting to measure velocity along the float tracks, we have to make one last step of computing the derivative using a first order central difference scheme applied to that smooth position data. And so here's an example of the velocities estimated along one of those buoy tracks with the acoustic estimates in orange compared to the true velocity computed from the GPS track in gray. We can see that they match really well. Again, we can compute the error statistics over the track of all 5 surface buoys, and we find that 90% of our measurements are within 0.12 meters per second of the true velocity during this deployment, which, given the nominal velocity of 1.4 meters per second, is less than 10% of the nominal sight speed. So to summarize our localization performance, we've demonstrated position accuracy within 5 meters. we've got velocity error less than 10% of the nominal water velocity in high flow situations. While I didn't explicitly cover it here, we've observed a practical range limit of about 1 kilometer in our benchmark tests. And we do see localization degradation due to poor array geometry shown here, as well as from sound speed gradients observed in Lake Washington that I didn't have time to discuss. Finally, the microfloat design that I presented earlier and the subsystem benchmarking tests are all in preparation to be submitted to the Journal of Field Robotics. And again, I'll pause here to see if people have questions about the localization accuracy.
Trevor, one question about how the change in speed of sound with temperature affects the position of the microfloats. I think this is getting at the Lake Washington data.
Yeah, it's rough. This has been a big challenge. I spent a lot of time with the Lake Washington data set, and I think I'll actually defer that question to the end, and I'll come back around to it and actually show some of that data.
Okay. No further questions, so continue.
All right. So having gained confidence in the accuracy of the depth control and the localization data, let's take a look at what we observe using the whole float swarm. So we're going to look closely at the Agate Pass tests in detail, where we went out last August and performed a series of surveys, including 4 during ebb, where the water was moving from Port Orchard out into Port Madison and the main body of Puget Sound, and then 5 on flood with the currents running the opposite direction. So during each of these surveys, we deployed the swarm of 20 microfloats and 5 localization buoys. And I was looking to evaluate the float measurements against those more standard methods. So we also used a vessel-mounted ADCP to perform station keeping surveys, as well as SWIFTs. These are drifting surface buoys equipped with a downward-facing ADCP developed by Dr. Jim Thompson in Civil and Environmental Engineering. So the floats were programmed to go to various depths for 20 minutes and then surface for recovery and redeployment. During that time, the station keeping vessel would take 5 minutes of data at each of the 3 locations indicated by those black dots. On flood deployments, the drifting devices were deployed roughly following the template here, and the 20 floats deployed at approximately equal intervals across that yellow line. The template on ebb deployments was quite similar, though a bit more spread out. So what does the resulting float swarm data look like? Well, let's take a look. So here's a video from the second ebb deployment. So there the floats dive to depth. This might be a little choppy, but here they are flowing downstream at their various depths. Take a look from above. You can see those 2 out in front. Those actually stayed on the surface due to a programming error, but they're moving faster. You can see there's a bit of a velocity gradient, and then they go back to the surface and finish off waiting to be recovered. So how do the floats compare to other devices? How do our measurements compare? First, let's take a look at the nominal velocity over the duration of the test at the second station keeping location. Here we observe excellent agreement from all 3 devices, and they match the NOAA prediction for the site quite well as well. Note that the gaps here in the float data in the middle are due to insufficient sampling near that station keeping location during that survey period. So next, we'll examine the float's ability to resolve vertical profiles. Here we're going to take a look at the data at station keeping location number 1. So in this case, I'm showing velocity on the x-axis and depth on the y-axis, and we see decent agreement between the floats and vessel, except at very near the surface, which I believe is an interpolation artifact. So in this case, the SWIFTs had insufficient sampling near the station keeping location, and they were excluded. Now, looking across all the surveys, we can see that all 3 devices match really well when there is sufficient sample coverage. When I saw this plot, I got really excited. So because both swifts and microfloats are drifting platforms, we can't fully control their sampling distributions. So here I'm comparing samples from the swifts and floats during that second ebb deployment. And in this case, they're moving north through the channel. And we can visually observe that the floats provide improved horizontal distributions. This is owing in a large part to the fact that there are more of them. Note that the gap in the Swift data is due to a burst sampling interval where the device gathers data for 8 minutes and then needs to take 3 minutes to process that data. So that produces that gap. Now, the floats provide that improved horizontal data, but if you look at the samples from the side, we can see that when the Swifts are sampling, the ADCPs provide a full profile to the full water depth, while the float samples are actually restricted to those pre-programmed depths. Now, to expand on the profile comparisons I showed earlier, we interpolated the float data to the locations of all the Swift samples and then examined the resulting statistics across all the surveys. So how do those velocity estimates compare? Well, excuse me. We look at the difference between the float and the Swift measurements. And this is the distribution of that difference, where the white bar is the median difference, the thick bar is the interquartile range, and the thin bar is the interdecile range, or the 10 to 90th percentage of the samples. Taking the median absolute difference as the representative metric for each of these distributions, we can normalize that error by the nominal water speed during the survey, and that gives us the percentage difference. And doing that, we can see that the float measurements match the Swifts to within 10% of the nominal speed, with the exception of slack tide, E4, when the overall velocity of the flow is just really low. And then another bit of information or evidence to the flow following nature of the float. I'm going to show a video here. You'll see the floats moving out the south end of the channel into Port Orchard. As they get into the body, those on the southern edge are going to move slower. We're going to zoom in on that box, and you can see those enter and eddy, creating looping tracks. And then at 20 minutes, they return to the surface and re-enter the flow. So this really is strong evidence of the flow following nature of the microfloats. So lastly, one of the major outcomes from the simulation work was that suggestion that the floats map in situ properties as well. So let's take a look at some of the data from our temperature sensors from these tests. So first we'll look at whether the floats can resolve vertical gradients. When we deployed in Lake Washington last summer, they also, we took a measure of water temperature using a conductivity temperature depth sensor, the result shown here. So temperature is on the x-axis and y is on the and temperature is on the x-axis and depth is on the y. And there's a really strong thermocline that day. The surface water is about 18 degrees Celsius warmer than the water at depth. And I'll comment that the two lines are from the device being lowered and then being raised, and the discrepancy results from the response time of the temperature sensor. Now let's look at results from a single microfloat over all the profiles it performed that day. And this is actually overlaid on the CTD data. You just can't see it because it nearly exactly matches. And again, note that the data is colored by the float velocity. So it's moving down when red and up when blue. And it's nearly white when it's holding depth. And we can see that this nearly matches the signal from the CTD. And if we plot all the data on top of from all 14 floats, you can see that it's very consistent. So what about horizontal temperature gradients? In Agate Pass during the flood deployments, we noticed a really interesting horizontal distribution where the samples on the north side of the channel were about 1.5 degrees warmer than temperatures on the south side of the channel. And while the overall mean temperature decreased over the flood period, the horizontal distribution remained consistent. And I don't have sufficient data to determine exactly what caused this, but it does suggest that there's water entering from two different source regions. So if we look at the broader map of the area with a survey area indicated by that white box, I'm going to hypothesize that there's possibly cooler water entering from the main body of Puget Sound, while there's warmer water coming down from along the Kitsap Peninsula, perhaps having been previously warmed in the shallow waters of Miller Bay. But I'll remind you that this is conjecture, but it was a really interesting result. So what can I confidently state from these results? Well, first, our measurement platforms agree to within 10% of the nominal velocity. So this is encouraging in terms of the scientific relevance of the float. The float swarms can resolve both vertical and horizontal velocity gradients, albeit with variable sampling distributions. The float swarms simultaneously map in situ water properties like temperature. And all of the field observations from Agate Pass are currently in preparation for publication. So with that, let's take a look back at the primary contributions of this work. First, I showed in simulation that the float swarms are a viable sensing paradigm for coastal scale phenomena. Second, I developed the microfloat swarm system, which is suitable for distributed sensing in coastal environments. Third, I detailed the benchmarking of the depth control and underwater localization systems to prove out the scientific relevance of the platform. And then finally, I demonstrated that scientific relevance with a swarm deployment in Agate Pass, doing a site characterization of the currents. So what's next? Well, encouraged by the success in Agate Pass, mapping those tidal currents, we're moving forward, expanding the capacity of the floats to support new applications. So this includes the addition of a conductivity sensor for study of river plume mixing, the addition of a hydrophone to investigate marine acoustics, which could include both biological and man-made noise. And eventually we'd like to include biologically relevant sensors like dissolved oxygen sensors to support research on algal patches and phytoplankton blooms. And finally, with improved endurance and autonomous swarm management, we can improve the endurance and duration and spatial scales resolved by the microfloats and fulfill the long-term vision of enabling a robust, flexible, and economic distributed sensing in coastal waterways. And with that, I need to express a lot of gratitude. First, to the funding agencies that enabled this work. Second, to my committee who've provided font of good advice and guided me along this journey. The float would not exist without the help of Corey Crisp, who really did the backbone of the electronics and software and made sure it was functioning and dealt with my crazy ideas. Jessica Noe contributed tremendously to the revised mechanical design of the new float, the modern version, if you will, and did her master's looking at potential control improvements to do a better job than that PD controller I'm using. Furthermore, a host of additional people, Zach Tully for deployments in Agate Pass, Paul Murphy, the bottom left there, who was a great roommate and also supported a bunch of different acoustic processing for the floats. Ben Maurer and Cassie Riel for their help on the disturbance tests. My girlfriend Ariana in the bottom center for joining me on the mid-COVID deployments, and Alex DeClerc for also doing a decent number of the drives out in Lake Washington. Additional thanks to the Agate Pass team field work, various help building from a number of individuals, conversations with others. I had 3 undergrad senior capstone design teams that worked on the microfloats in different capacities. Testing support from a number of UW people and fabrication from these shops. And obviously a huge thanks to all of my friends that have helped me along the way and made grad school not just about putting things in the water. You've made it certainly a much more enjoyable experience. It would have been nice to be with you for these last year and a half, but luckily I'm not going anywhere. I'm sticking around at APL, so I'll get to see more of you. And then thanks to my family, last of all, not least of all, most of all. It's been a rough couple of years. My dad's didn't quite make it around to see this event, and I dedicate this talk to them. But it's been a process, and I'm really excited to be at this point. So thank you.